Let's take a look at the lawnmower blade model and use solid edge simulation to digitally validate the design. One of the biggest challenges in simulation is defining the boundary conditions correctly. Solid edge simulation includes a full complement of load and constraint definitions to realistically model boundary conditions. Loads and constraints are geometry-based and easily applied from the quick bar. In this analysis, we'll look at the model's natural frequencies initially, so we won't apply any loading at this stage. As this is an assembly model, we need to specify how the components interact by defining the type of contact. Solid edge simulation has automatic contact detection and provides realistic contact behaviors with either glued or linear contact, so you can quickly and easily set up the assembly model. Next, we'll mesh the model, and for the sake of expediency, we'll pick up on a mesh that's already been created. Solid edge simulation provides a lot of control over mesh creation, and each component can be meshed independently. For example, here we've given the blade a much finer mesh than the rest of the model to more accurately capture its bending behavior. For dependable, high-quality results, solid edge simulation incorporates the industry-standard NX Nastran solver. The plot shows the displaced shape with a strain energy density contour for one of the natural frequencies. For each of the modes calculated, we can view the associated displaced shapes. Solid edge simulation provides several analysis types to allow you to investigate various physical behaviors, and in this case, we'll now switch from a modal to a linear statics analysis to investigate a blade loading case. As with constraints, loads are geometry-based, and solid edge simulation provides various types of physical loading. In this case, we'll apply a simple force, but see how you can use the solid edge steering wheel to help position and orient the load by referencing surrounding geometry. With the loads and constraint definitions completed, we'll clear up the display and switch them off. As we've already run an analysis using this model, with solid edge simulation, we can pick up the previous mesh and use that, saving duplication and model setup time. With the analysis complete, we can look at some of the results. This plot shows a displaced shape with the von Mises stress contour. With solid edge simulation, you have several options for displaying the stress contours, with continuous or distinct contour bands or by element. You can also animate the displaced shape with the stress contours, which helps to interpret the results and gain understanding of the model behavior. The applied loading puts the shaft into bending, and the stress levels are higher than desired. So by validating the design digitally, we've identified a problem, and it's early enough in the design cycle that we can fix it quickly and efficiently with solid edge simulation, and without having to build any physical prototypes.